Welcome to the video called USearch Products. In this video, I will talk about 6 USearch products: histograms, time series, return period analysis, geospatial or mapping analysis, sea level rise analysis, and our multimedia archive. So let's jump right into histograms. So histograms basically are graphs where we take extreme events and we plot out the highest magnitude event, which we rank as event number 1, and we rank all of these until we get to our lowest magnitude event, which in this case we rank as 39. So this means we have 39 storm tide events at Corpus Christi, Texas. This is from 1900 to present. So we've just basically plotted these out according to their rank and height. And this is our height above NAVD88. This is a vertical datum or vertical reference mark above which we're measuring the water level. And so in this case, let's go from right to left. What we see here, and this is pretty common pattern when we plot out extreme events, there's really little slope or little change among these lower magnitude events. In other words, the height of event number 25 and 26 are pretty much the same. However, when we move up into these more rare events, we see the slope starting to increase. This big jump here for Corpus Christi, if you can see between events 6 and 7, there's a big jump. Over time, as more data come in, we will actually see this smooth out. But sometimes we'll get these jumps because of randomness in the data. However, we can see these top 6 events here are definitely higher magnitude than the others. And this number 1 event from the hurricane in 1919 really stands out from the others. In fact, it kind of stands out. It's something that our eyes go to when we look at this graphic. We may think that that's an error or a mistake in the data or a real anomaly that will never happen again. However, when we look at statistics for extreme events, we see this pattern a lot where the highest magnitude event or the highest maybe 1 or 2 magnitude events are often much higher than the others. And if I was given one topic to talk about related to coastal flooding, I would talk about this topic, the idea that the most extreme events are much higher than the others. This takes a lot of people off guard, and this concept is responsible for a lot of deaths and destruction of property because sometimes we really underestimate the risk of coastal flooding and other geophysical hazards as well. So let's look at other examples. It's not just with hurricanes and storm surge that we see this type of statistical distribution. We see it in many different types of data. This is a graph of $10 billion weather and climate disasters in the U.S. from 1980 to 2016. So we've had 23 events that had at least $10 billion in losses. And again, this idea with the distribution, these lower magnitude events really are very similar to each other. When we get up to these higher magnitude events, we see the slope starting to increase. But this event here, the number 1 event, Hurricane Katrina, $153 billion in losses converted to 2016 dollars. The losses for that event are more than twice as high as event number 2, which is Hurricane Sandy in 2012. And so really sometimes 1 or 2 events can really stand out from the others. We don't just need to look at weather or climate data as well. We can look at sports data. If you look at the leaders in different sports, we'll often see that. Here's an example from population data. So I took the population of cities in Massachusetts from the 2010 Census Bureau, from the Census Bureau in the 2010 census. And what I've done here is I plotted out the population of all cities with more than 40,000 people. And again, these lower magnitude, between 40 and 50,000 people, we see a lot of similar populations. But when we move up to these higher populations, we see the slope start to rise. But the number 1 location, Boston, has more than 3 times as many people as the number 2 city in Massachusetts. And again, we can pick almost any state, we will see a pattern like this. You'll see cities like Atlanta, Georgia, Denver, Colorado, Chicago, Illinois will really stand out from the rest of the population. And so this is something that if you pick your favorite data to look at and you just look at the extremes. Again, we're not looking at the averages here. We're looking at the most extreme. We will often see this 1 or 2 events will really pull out from the others and really stand out. So getting back to coastal flooding, this tells us a lot about statistical distributions of coastal flooding in different areas. Coastal flooding is very localized, so when we move up or down the coast, these numbers will change quite a bit. Here in Corpus Christi, we see the slope really starting to increase here between like 8 and 10 feet. This number 1 event approached 15 feet. So this tells us something about the shape. If we were to do a plot like this in East Asia, we would see the numbers would be considerably lower because we have deeper offshore water. Getting a storm surge more than 10 feet there for a place like China would be extremely rare. We just may not see an event like this in the data set. So this can really tell us something about the statistical distribution. And I would make an argument that data-driven analysis here can do a very good job and in some ways outperform modeling analysis. And the reason I'm saying that is because to model this, really, we would need to make a set of assumptions about tropical cyclones, really our hurricanes, our tropical storms. How many events would we see? How strong would these events get? What would the tracks likely be? And so we would have to make a whole set of assumptions just about our tropical cyclones. And imagine if we modeled that perfectly, if our assumptions were right on, then we would still need to infer how much water those events would displace. So our storm surge modeling, we're really making assumptions on top of assumptions. And could we get, really close to this type of distribution? I don't know if we could. So at least a data-driven analysis deserves a look to actually look at more than 100 years of records for a location. I will say here in Texas, we've had a lot of these higher events that stand out. There are areas in the U.S. where we just have not really seen this outlier yet occur. I'm thinking of Western Florida. I'm thinking of places like Northeast Florida, Georgia, South Carolina. We've seen an active tropical cyclone climatology there in the late 1800s, but since 1900, we haven't. And so there are places like Tampa, Florida, where we don't quite see this outlier standing out here yet. Models suggest that we could see a 20-foot or a 6-meter storm surge in a place like Tampa. So probably the best approach is to use modeling coupled with a data-driven approach. In many cases where we have robust data, we're going to be able to really fine-tune and really get a good idea about storm surge risk in those locations. We can also learn something about perception of coastal flooding for the people living in a given area. I took the Corpus Christi data here, and I color-coded these based on time. Everything in red here happened since 1981. So let's imagine that you moved to Corpus Christi 36 years ago. In 1981, you've seen a lot of weather. In fact, you've seen 23 events here, coastal flooding events that we've recorded. That's about 1.5 events per year that was a slight mistake. I'm sorry, that's an event I think every 1.5 years. So again, you've seen a lot of events over time, but all of these coastal flood events come in between 2 and 5 feet. You haven't seen any of these higher events. And the concern there is that in places like South Texas, where they just haven't seen really any major coastal flood events in a long time, people may feel very familiar with the weather, with the different flood events that they've seen, and they may think that a 5-foot storm surge is as high as it gets because they just haven't seen anything higher than that over time. A time series is also helpful to look at this. So this is taking the same Corpus Christi data, and I put this in our product number 2 here, time series. This is looking at time from 1900 to present. This is the height in water level above NAVD 88. And again, these 6 extreme events really stand out. The highest event here we see now was in 1919. So nobody alive today remembers an event that occurred nearly a century ago. So some people obviously would remember some of these events, but a lot of the population either is younger than, say, 40 years old, or they moved to the area in the past 36 years. And so this is all that they would remember, these events here. Something else I wanted to point out is the influence of sea level rise. When you can really see it on these time series. The sea level here is this blue polygon at the bottom. But look at these lower magnitude events. They're very numerous. Again, we see these 23 events since 1981. But again, we see a lot of these events, and they seem to be, if you look closely, there seems to be a trend here, a slowly increasing trend, which sort of mirrors the sea level rise trend. These events have approached 5 feet. The highest was 4.94. So if I was interested in a property that's 5 feet above NAVD 88, that property would not have flooded from storm surge yet, from these lower magnitude storm surges, I should say. However, in the near future, we get the impression that this threshold will be exceeded, and when it's exceeded, it may be exceeded quite frequently. So we may have areas that have not been flooded from these lower magnitude storm surges that are going to start to be flooded maybe 2 or 3 times per decade. That's very interesting, and that definitely is a climate change trend, as well as we have subsidence in coastal areas. These higher magnitude events, I really think that has more to do with randomness over time. We don't necessarily see a trend in a lot of locations as far as these higher magnitude events, but the lower magnitude events we do, they're so closely really coupled with sea level rise there. So just this can give us some interesting information about coastal flood risk. Talking about sea level rise, what we've also done is taken sea level rise predictions. So There are various sea level rise scenarios that are in written up reports, in peer-reviewed papers, in IPCC reports. We can take those levels, which are often given for sea level rise scenarios out to, say, the year 2100, for example. We can take those levels, and then we have fit mathematical equations to those future levels. And so we can pull out any year in the future and give a good idea based on a high rate of sea level rise, medium, and low, what various sea level rise scenarios may be for each location. This here for South Padre Island, Texas. And so that's something that we include in our analysis. And then also return period analysis. I've spoken about this in some of the other videos, so I won't go into too much detail here. But what we can do is take a comprehensive data set. So this is for South Padre Island. This is looking at the events there that we have in the record. The highest event was Hurricane Beulah. So we have 117 years of data here from 1900 to 2016. So Beulah was the highest magnitude event in 117 years. So we go here to about 117. We go up to 12 feet, which was the magnitude of Hurricane Beulah. And we plot this blue diamond here. This is an actual observation. The second highest event here was from the 1933 hurricane. The storm surge level was about 11.2 feet. And what we do is we take the period of record, or 117 years, divide it by 2, because this was the second highest event in 117 years. So we go to about 58 here and we plot that. This is the actual plot for the 1933 storm surge event. So on and so forth. We plot out all of these blue diamonds, and the black line here is the line of best fit, or the regression line. We get a pretty good fit here. The R-square is about 0.98. What this tells us is that the 100-year water level from storm surge near South Padre Island is about 12 feet. So that means on average we should see a 12-foot storm surge on average every 100 years. Level should equal or exceed that level every 100 years, I should say. So this is really useful for validating models and seeing if models maybe underpredict future water levels. If a storm surge model said that the 100-year storm surge near South Padre Island was around 10 feet, we might think that that's underpredicting, because we've had 2 events in the last 117 years that exceeded that level. And also, taking a comprehensive data set together, running statistical analysis, we see a 100-year regression level here of about 12 feet. So this is good for validating, especially if a model underpredicted water levels. That would become pretty evident here with our analysis for return period. And also, so we may have these levels, for example, a 12-foot storm surge every 100 years on average. We may have those levels, but what do they actually mean on the landscape? What does that actually flood? What is the impact? That's where our 5th tool, geospatial analysis, comes into play. What we can do is actually map out these water levels. So what is the water level for the 200-year storm surge or the 100-year storm surge? We've brought a new member onto our USurge team. Nick McIntyre has done a lot of this work. Nick is our technical guru and surfer dude. Nick is amazing with geospatial analysis, GIS. He really is a good hardcore computer programmer, and he can take these levels and map them out according to elevation data. And another thing that we actually do is we include the sea level rise analysis in this mapping analysis. So if you're interested to map out, what's the 100-year storm surge, but 50 years from now, we can do those adjustments. That's something that FEMA does not do, but we really feel that we need to include both these extreme water levels, these 100-year surges, but also sea level rise out into the future, because all these lines will shift over time, moving inland as sea levels continue to rise. Finally, our 6th tool is Multimedia Archive, and this is important. We can see these numbers on paper or on a graph. We can see a 3-foot storm surge or a 10-foot storm surge, but what does that really mean? We have a multimedia archive for each city where we can actually look up an event and actually see a video or picture of many of these events, what they actually did on the ground. For example, South Padre Island, Texas, Hurricane Ike produced a 3-foot storm tide, and this is what it actually looked like. So when we hear of a 3-foot storm tide, that doesn't sound really too impressive, right? We may just picture 3 feet of vertical flooding above the ground level. However, when we look at the video here, we see a lot of waves. We see the waves and the currents and a lot of dynamic water moving around, hitting the seawall, hitting the dock there, also a lot of erosion. So our multimedia archive can be really linked to these events to give us an idea of what does it actually look like when a storm surge level of a given magnitude inundates an area. Anyway, that's everything. These are our 6 tools, and would love for you to give us a shout out. Send any questions or comments you have. You can always email me at hal@marineweatherandclimate.com or go to our website, www.usurge.net. We'd love to hear from you and hear what your needs are and how we could help meet them. So thanks again for tuning in. Again, my name is Dr. Hal Needham. Thanks so much for your time and attention, and let's keep in touch and keep looking at our risk along the coastlines. Okay, take care.